Alright, so this last thing from section 5.2, which we went over undoing the chain rule, right? Finding the antiderivative of a function whose derivative was found by the chain rule, right? Well, the last part of this is a special case of that substitution rule that involves the natural log function and the chain rule. And this one actually has a theorem that really you just have to recognize and remember what the derivative of the natural log function gives us. So if you remember, the derivative of this function, dy over dx, is 1 over what's inside, so 1 over the inside function x cubed plus 5 times the derivative of what's inside, 3x to the second. And then if I rewrite that, I get the fraction x cubed in the bottom plus 5 over its derivative, or under its derivative, 3x squared. And so this is the differential equation we're going to look at. All right, so if I were looking, the derivative of a natural log that involved composition, or again, the chain rule, function inside another function, where my natural log is the outside, and the derivative is the inside, well, we always get the ratio. All right, so the answer to the question is this below. This is what we always get. When we have the derivative, when we have the function, the natural log of a function, right, that's what a composition means. It's the natural log composed with another function, natural log of f of x. When we take the derivative of that, it's always what's inside. All right, 1 over what's inside times the derivative of what's inside, which can be rewritten as this fraction. All right, so the derivative that gives us this, so again, remember, antiderivatives are what we're doing. So I need to recognize what function gave me this derivative. So if I get a differential equation that's inside my integral, that's the derivative of the denominator in the numerator, well, the only possible function that can give me that derivative is my natural log. And so this is the ratio we've got to recognize. And so that's what we get. We get actually the following theorem, which can be shown using the substitution rule. But you don't have to use the substitution rule. If you just remember this theorem, that's really all you have. So it's kind of just check, do I have this ratio? All right, do I have this fraction where the numerator is the derivative of the denominator? If that's the case, then the antiderivative of the original function had to be the natural log. Now, we leave absolute value because, remember, this function that's inside my integral may have negative values, right? And so to get around that, to make sure, unless, I have to say only for f of x positive values, we get around that by always doing the absolute value. So whenever we take the antiderivative of a natural log, just remember, an absolute value is always involved. It is the substitution rule, but it's a very special case where we have a theorem for it. So again, it is shown or solved by the substitution rule. Right, if I start off with this ratio, I can rewrite that fraction as 1 over the f of x function times the derivative of f of x. All right, all I did was rewrite it. All right, so rewrite the fraction to give me the expression that I want. This would be the u part. All right, that's inside the 1 over the fraction, the 1 over my function. This is the derivative of the inside, so that would represent the du part. And so when we substitute that out, I'm left with 1 over u du. Well, 1 over u is the derivative of the natural log. So the natural log of u with the absolute value. And then again, we'd substitute back and get that original expression. So it'd be the natural log of the absolute value of my denominator function plus my constant is the family of antiderivatives, or the family of possible function that gives me out this function's derivative. Right? If I took the derivative of this, right, I get 1 over what's inside times the derivative of what's inside. Right? And so whenever we have this ratio, so this is my check. If I ever have an expression that looks like this, there's no work to be done. Right? All I do is sort of check that off, check that that's true. If that's true, then my antiderivative has to be the natural log of the denominator. And again, we always take absolute values because natural log can only be positive inside, plus some unknown constant. Alright, so now we're just going to kind of practice this special rule. Alright, so again, the check is this the ratio I'm given in that fraction? Does this check? If I take my denominator, the derivative of my denominator, right, so if f of x is e to the 2x minus 10, if I take its derivative, is that my numerator expression? Well, the derivative of e to the 2x, well, is e to the 2x times 2, right? That's the chain rule. It's the e to the 2x times the derivative of the inside, which is 2. The 10 will zero out, and I can rewrite that with the 2 in front, and that checks. That is my numerator, right? And so that means, I guess I should say that checks, and so that means the only possible antiderivative of this would be the natural log of the function inside, which I need to take the absolute value of it, because there are negative numbers here, right? Because of the minus 10, I can get out negative numbers, so I can't plug negative numbers in my natural log, so we put the absolute value, and then there's that unknown constant. And so that's my answer. Alright, that's the answer to this indefinite integral. Natural log of the absolute value of e to the 2x minus 10. Alright, next example. Alright, same thing. I want to check this one to see if I get the same thing here. The derivative of my bottom function, the denominator, is in my numerator. And so the bottom function was 3x plus 5. The derivative of that, well, the derivative of 3x is 3. The 5 will zero away, and so it checks, right? And so since that checks, the only answer possible is that the antiderivative of this is the natural log of the absolute value of that 3x plus 5. And don't forget there's that constant, because I want all of my possible antiderivatives, and that's all of my possible antiderivatives. Alright, so these are pretty straightforward. The only time there's a catch is sometimes I have to manipulate my function to get what I want, and this is an example of that case. Alright, so remember, my check is, does this equal this ratio? Well, in this case, it's not going to be straightforward, right? If I have my bottom function, which is the x squared minus 3x plus 4, I take the derivative of that. Alright, well, the derivative of x squared is going to give me 2x. The derivative of the negative 3x is negative 3. The 4 will zero out. And so the real ratio that I want would be the 2x minus 3 over that x squared minus 3x plus 4. But that's not what I was given, right? I was given 4x minus 6. I need 2x minus 3. Well, what can I do to the 4x minus 6 to give me 2x minus 3? Well, what if I factor out a 2? Right? If I factor out a 2 out of that expression, right, and so I'm going to go below it. Right? If I factor out a 2, it means it's pulling a 2 out front 2 times. So I pull out a 2. That's going to leave me with a 2x, right? I'm dividing it out. So 4 divided by 2 leaves me with 2. 6 divided by 2 leaves me with 3. Alright, now I've got what I want, but there's an extra part to it now. Alright, the extra part to it now means it's not, I have a 2, right? That 2 is out front, and so it doesn't go anywhere. I just can't throw it out. I can't get rid of it. I have to keep it, and so that means there is an extra constant. And so what I have is 2 times the derivative of the bottom function divided by the bottom function, right? And so this 2 is just the constant that's going to come along. And so when I take my antiderivative, it's 2 times that expression that I want. All right, and so now I have the expression I want, right? That's the expression I want. There's just an extra constant that comes along, and the extra constant is part of the answer. It doesn't disappear. All right, it's going to be 2 times the natural log of my denominator, right? My x squared minus 3x plus 4. And then that constant at the end, all right? So there is my general antiderivative. If I take the derivative of this function, I do get back to this expression. And so this one I had to do a little work And by a little work, that means I had to factor out a constant. And the constant doesn't disappear. It comes along as a constant multiplier, right? That 2 comes along, and it's a part of my final answer. And it's out front of my derivative, or antiderivative. It's out front of my antiderivative. Alright, and so again, that's the only type where you'd have to do something like that. You might have to factor out a number. And remember, the number doesn't disappear. For some reason, students will like to factor it out and then forget about it. You can't forget about it. It's still a part of the answer. Alright, so don't forget about it. Alright, so that finishes up 5.2. So do make sure you look at those and practice those. We'll stop there.